All right, so we're going to finish up chapter 10.1 and talk a little bit about converting equations, and then we're going to do one final thing that we touched on a little bit earlier, but I wanted a chance to summarize. So we're going to start with converting rectangular form equations to polar form. So the thing to keep in mind is that we know that x equals r cosine theta and y equals r sine theta. And this is actually the majority of what we need to do. So we can start off by plugging in if x equals r cosine theta, then we get r cosine theta plus 3r sine theta equals 8. And from here we can just, we could pull out an r, so we could say r times cosine theta plus 3 sine theta equals 8. And we can leave it like that because this is an equation that is of the form FR theta. So this may not seem like it's simplified, but this would be, this is a good form to leave it in. Okay, let's try this one. So we're going to convert x squared equals 8y to polar form. So we can write this as r squared cosine squared theta equals 8r sine theta. In this case, I would bring my r here, and I would do 1 minus sine squared theta minus 8r sine theta, giving me r squared minus r squared sine theta minus 8r sine theta, equals 0 up here, equals 0. And I mean, I think you could leave it in this form. Even this form would probably be okay. I just wanted to convert everything to sines and leave it all on one side. All right, how about this one? 6xy equals 1. So for this case, we would have 6r cosine theta, r sine theta equals 1. And this is 6r squared cosine theta sine theta equals 1. So in this case, this is a pretty good equation, but this actually looks like something that we've seen before, and we can actually simplify this a step further. So we'll say that this is 3r squared times 2 cosine theta sine theta equals 1. And we recognize this piece as our double angle for sine. So this is 3r squared sine 2 theta equals 1. Okay? For our final rectangular to polar, we have r cosine theta equals -2. You could bring it to the other side if you wanted, r cosine theta plus 2 equals 0. But we've now got it nice and converted. So the idea is that we're just plugging in x equals r cosine theta and y equals r sine theta, and just seeing if we can, catch an identity or something like that. So I think these aren't too bad. So let's try converting from polar to rectangular. So we have r equals 6, right? And we want to convert that to rectangular form. So let's start off by plugging in the fact that we know r is the square root of x squared plus y squared. So we get the square root of x squared plus y squared equals 6, or x squared plus y squared equals 36. Now you may recognize this as a circle with radius 6. And in fact, that is exactly what we have up here. So r equals 6 is just telling you that this is a circle of radius 6, and when we convert it into rectangular form, we get the same thing. But this is an interesting example. I said earlier that in some instances, polar coordinates are a lot simpler and cleaner than rectangular coordinates, and this is one of them, right? R equals 6 is just telling you a circle of radius 6, and x squared plus y squared equals 36 is telling you the same thing, but one of them is a lot cleaner than the other. So let's try the second one. R equals 8 sine theta. So for this one, it's probably going to be easier to start off by multiplying both sides by r. So you get r squared equals, 8 r sine theta. Now the point is that when we have this r squared, we can rewrite this as x squared plus y squared. And look at this r sine theta, well, that's just y, right? So this is 8y. So we can bring it over and we'll get x squared plus y squared minus 8y equals 0. So we'll rewrite this as x squared plus y squared minus 8y equals 0. Now here we're going to do something called completing the square. So the idea is we're going to take this, we're going to divide by 2, and this coefficient, this -8, right? We're not taking -8y, we're taking -8. So we're going to divide by 2 and square it, then add it to both sides. Now, the reason we do this is because we can then write this as x squared plus y squared minus 8y plus 16 equals 16. Now, you may recognize that this is x squared plus y minus 4 squared equals 4 squared. So what is this telling us? This is telling us, oh, excuse me, there's a plus here, that this is a circle with radius r, radius r equals 4, so radius 4, centered at x equals 0, y equals 4. So this is a similar example where we have this whole equation, x squared plus y minus 4 squared equals 16, is just telling us about a circle, and that can be written as r equals 8 sine theta. So one of these is a lot more compact and a lot easier to work with than the other. And this is another example in which polar coordinates are easier to work with than rectangular coordinates. So let's real quick go over, we began talking about it with this problem where we were kind of showing how you could get multiple points from the same, or excuse me, you could have multiple positions on the coordinate system that are different points, right? And the idea being that because these are circles, right? We're going to run into the same point, the same position over and over again, but the point is going to look like a different form. So we saw, right, that you could go in the positive direction for theta, or you could go in the negative direction for theta. But let's do another quick example of this. Supposing I had the point 1 pi over 2. So the idea is that I walk over 1 unit and then sweep over pi over 2 degrees. So how many different ways can I write this point right here, point P? Well, I could also, we'll keep it down here. I have 1 pi over 2. I could also go over 1 and then sweep over, I'm going to do this in a different color, sweep over -3 pi over 2, right? So I could do it as P1 -3 pi over 2. What if I wanted to do it where r is less than 0? So in this case, I could write it as p negative 1. And so in this case, I am going to go over 1, right? So we treat it as normal. And I want to end up down here. So that means that I could go all the way over to 3 pi over 2. The idea being that I go over 1, swing all the way around 3 pi over 2, and then now I walk backwards, right? I walk in the opposite direction. That's how we did it before. You treat it as if you are in the positive, right? You walk positively, and then at the very end, you then walk backwards. And that's how you plot it when you have a negative r. So that's exactly what we did. We walked a distance of 1, and then we knew that we wanted to end up at this point up here. So that means that I wanted us to swing around to end up here so that when I walked backwards, I'd walk up. So this is p negative 1, 3 pi over 2. Another point we could do is to walk negatively. So we could do p negative 1, negative pi over 2. So in this case, I would, since it's negative 1, I'm going to walk positively, move negative pi over 2, and then walk negatively to end up at the exact same point. So the idea here is that all of these points are going to end up in the exact same place. Here's where it gets even more fun. I'm going to draw it right here. So let's say that I'm at this point. This is 1 pi over 2. Here's the thing. If I go, instead of just pi over 2, I go 5 pi over 2, I end up at the exact same place. So this could also be p1 pi over 2 plus 2 pi, because I've gone a full circle. Similarly, I could do 1 pi over 2 plus 4 pi. You're probably beginning to see what I'm getting at. I can also write this as pi over 2 plus 2k pi. The idea being that because we're thinking about these things as, concentric circles, the idea is that I can just keep coming back to the same position, right? We have to be kind of careful with the word point and position. If a point is uniquely denoted, right, then it's not the same point, it's the same position with different points giving you the same position. The idea being that all of these points look different, but they end up at the exact same position. So there's a summary on page 763 that talks about the fact that a point, r theta, can be represented by any point that has the form theta plus 2k pi, or 2 pi k as your book writes it. But remember, we could also go with a negative r, right, just like we did up here. So we can also write this as negative r theta plus pi plus 2 pi k, where k is an integer. So as we can see, this is going to be an infinite number of points that end up at the same position. All right, so that is our introduction to polar coordinates. I really wanted to make sure that we hammered down this idea. We started talking about it a little bit earlier, and I mentioned that there was a fourth point. But I would have to think about that because it's a little complicated when you're switching the r. R is less than 0 and theta is less than 0. But I think this is a good example that just a simple example that shows how all 4 of these are going to get you to the exact same position in the coordinate system, and then further that these tell you about the fact that you can actually arrive at that same position with an infinite number of points that look different, right? Because you're going to add 2k pi, or flip the r, or something like that. So polar coordinates are really interesting in that regard. Next chapter, we're going to be talking about graphing polar coordinates, and then it's going to become really obvious, I think, how powerful these polar coordinates are because they repeat, right? They're more complicated because in rectangular coordinates, each position has exactly one coordinate, right? 2, 2, there's no other way to write 2, 2, right? You can't come back to 2, 2 or anything like that. But in polar coordinates, as we see, there are an infinite number of ways, an infinite number of points that are going to land you at the same position on the coordinate system. However, as we'll see, that actually allows us to graph some really cool stuff.